Hey cosmic explorers, and welcome back to the channel. Tonight, we're diving headfirst into one of the most mind-bending, awe-inspiring, and frankly, terrifying objects in the entire universe, the Magnetar. Imagine a star, but not just any star. A star so incredibly dense, so impossibly magnetic, that it makes black holes look almost quaint by comparison. We're talking about magnetic fields so strong they could rip you apart atom by atom from 1,000 miles away, or erase all the data on every credit card on Earth in an instant. These are the titans of electromagnetism, celestial lighthouses whose beams cut across unimaginable distances, carrying whispers of their extreme existence. But what exactly is a magnetar? How do these cosmic monsters come into being? Do they have a purpose in the grand tapestry of the cosmos? And what happens when their intense, volatile lives finally come to an end? For centuries, humanity has looked up at the night sky and wondered. We've mapped constellations, charted the movements of planets, and even dared to glimpse into the heart of distant galaxies. But some of the universe's most profound secrets remain hidden, tucked away in the extreme corners of physics. Magnetars represent one such secret, a testament to the raw, untamed power that can be forged in the fiery crucibles of stellar death. They are not just theoretical constructs. We have observed them, detected their powerful emissions, and continue to unravel the mysteries surrounding their existence. Their discovery has pushed the boundaries of our understanding of matter under extreme conditions, challenging established theories and opening up entirely new avenues of astrophysical research. Our journey today will take us through the birth, life, and death of these incredible objects. We'll explore the science behind their unparalleled magnetic fields, delve into the cataclysmic events that forge them, and ponder their ultimate fate. This isn't just a story about a star, it's a story about the absolute limits of physics, about how nature can create something so bizarre, so powerful, that it almost defies imagination. So, buckle up, because we're about to embark on an adventure to the very edge of stellar extremes, where the fabric of space-time itself is warped by forces almost beyond comprehension. Prepare to have your mind blown as we begin to uncover the secrets of the Magnetar. The Cosmic Cradle, Birth of a Giant. Before we can understand a Magnetar, we need to understand its origins, and like many of the universe's most spectacular phenomena, it all begins with a star, but not just any star. We're talking about a truly colossal star, one that dwarfs our own sun by factors of tens, sometimes even hundreds, of solar masses. These are the giants of the stellar nursery, burning through their fuel at an incredible rate, destined for a short but brilliant life. As these massive stars exhaust their nuclear fuel, primarily hydrogen, then helium and so on, fusing heavier and heavier elements in their cores, they eventually reach iron. Iron is a crucial turning point, because unlike lighter elements, fusing iron actually consumes energy rather than releasing it. This marks the beginning of the end. With no outward pressure from nuclear fusion to counteract the immense inward pull of gravity, the star's core begins to collapse with unimaginable speed and force. In mere milliseconds, an object the size of Earth can shrink to the size of a city. This rapid compression is so extreme that electrons and protons are squeezed together, overcoming their natural repulsion and forming neutrons. The core becomes an incredibly dense ball of neutrons, barely 10 to 20 kilometers across, yet containing more mass than our entire sun. This incredible transformation unleashes an outpouring of energy so vast it causes the star's outer layers to be violently ejected into space in a spectacular supernova explosion, an event so bright it can temporarily outshine an entire galaxy. Now here's where the Magnetar story diverges slightly from that of a regular neutron star. For a Magnetar to form, the progenitor star must not only be massive, but it must also be rotating incredibly rapidly and possess a particularly strong initial magnetic field. As the core collapses and its radius shrinks dramatically, the magnetic field lines that were embedded within the star get squeezed and concentrated. This is due to a principle known as magnetic flux conservation. Think of it like a figure skater pulling in their arms to spin faster. As the star's core collapses, its rotational speed increases dramatically, and critically, its magnetic field intensifies exponentially. This amplification is what transforms a nascent neutron star into the supermagnetized object we call a magnetar.
The heart of the beast, unfathomable magnetism. So, we have a neutron star, formed from the collapsed core of a massive star, spinning rapidly and carrying an amplified magnetic field. But what does amplified truly mean in the context of a magnetar? We're not talking about your refrigerator magnet here. We're talking about magnetic fields that are a quadrillion times stronger than Earth's magnetic field, and 1,000 times stronger than even the most powerful man-made magnets. To put that into perspective, if you were to stand just 1,000 kilometers from a magnetar, its magnetic field would be so intense that it would rip the electrons from your atoms, literally disassembling your body at a fundamental level. It's a force so profound, it's almost impossible for the human mind to fully grasp. This extreme magnetism doesn't just affect objects near the magnetar, it also has profound effects on the magnetar itself. The magnetic field is so powerful that it can actually deform the star's crust, causing star quakes, sudden, violent ruptures on the surface. These quakes are not like earthquakes. They unleash incredible amounts of energy, often in the form of X-rays and gamma rays, which can be detected across vast cosmic distances. These bursts are some of the most energetic events observed in the universe, second only to supernovae themselves. It's like the magnetar is constantly under immense internal stress, its very structure groaning under the strain of its own colossal magnetic field. The magnetic field isn't static either. It's a dynamic, evolving entity. Scientists believe that currents of charged particles within the magnetar's incredibly dense, superfluid interior generate and sustain this field through a process similar to a geodynamo, but on an unimaginable scale. These internal currents can tangle and twist the magnetic field lines, causing them to break and reconnect, similar to what happens during solar flares on our sun, but with vastly more destructive power. These magnetic reconnections are another source of the intense bursts of radiation that characterize magnetar activity, creating energetic flares that can last for hours or even days, bathing a wide swathe of space in their high-energy glow. The restless life, bursts and flares. The life of a magnetar is anything but quiet. Unlike stable neutron stars or pulsars that emit regular, predictable pulses, magnetars are known for their erratic and incredibly powerful bursts of energy. These aren't just faint whispers across the cosmos. These are cosmic screams that can light up entire regions of the sky in high-energy X-rays and gamma rays. Imagine a cosmic lighthouse, but instead of a steady, rhythmic beam, it occasionally lets out blinding flashes that momentarily outshine everything else around it. These are the soft gamma repeaters and anomalous X-ray pulsars, the two main classes of objects that scientists now understand to be magnetars. The cause of these dramatic outbursts lies in the magnetar's extremely powerful and constantly shifting magnetic field. As we discussed, the immense magnetic forces can stress the magnetar's crust, leading to sudden ruptures or star quakes. When these quakes occur, the energy released can be incredible. A single large flare from a magnetar can release more energy in a fraction of a second than the sun will emit in 100,000 years. This energy is carried away by a torrent of high-energy particles and photons, which rush outwards, traveling at nearly the speed of light, carrying the signature of the magnetar's violent interior to distant corners of the universe. Another mechanism for these flares involves the magnetic field lines themselves. The magnetic field, being so intense, can get tangled and twisted as the magnetar rotates and its internal plasma moves. When these twisted field lines become too stressed, they can violently reconnect, releasing vast amounts of stored magnetic energy. This process is analogous to solar flares on our Sun, but scaled up to an astronomical degree. These magnetic reconnections can accelerate particles to incredible speeds, producing the observed X-ray and gamma-ray bursts. The study of these bursts is crucial for understanding the extreme physics at play within magnetars, giving us glimpses into processes that cannot be replicated in any earthbound laboratory. Stellar seismology, quakes and oscillations. The concept of a star quake on a magnetar is truly fascinating and offers a unique window into these extreme objects. Just as seismic waves allow geologists to probe Earth's interior, the energy released during magnetar quakes allows astrophysicists to study the otherwise inaccessible interior structure and dynamics of these neutron stars. When the crust of a magnetar ruptures under the immense magnetic stress, it generates seismic waves that travel through the star's incredibly dense interior. These waves can cause the entire star to oscillate or ring at specific frequencies, much like a bell struck by a hammer. The detection and analysis of these oscillations are a cutting-edge area of research known as magnetar seismology. By studying the precise frequencies and damping rates of these oscillations, scientists can infer properties about the magnetar's internal composition, its equation of state, how matter behaves under extreme pressure and density, and even the strength and configuration of its internal magnetic field. For instance, the presence of specific oscillation modes can tell us about the thickness of the magnetar's crust, or whether there's a superfluid interior where particles flow without friction. It's like trying to understand the inside of a bowling ball by listening to the sound it makes when you drop it. The most powerful magnetar flares, often termed giant flares, provide the clearest opportunity for this type of stellar seismology. These events are so energetic that their afterglow can be observed for extended periods, and the oscillations they induce can leave detectable signatures in the observed X-ray light curves. While challenging to interpret, these observations are invaluable because they probe conditions far beyond what any terrestrial laboratory can achieve. Understanding how matter behaves in such extreme environments is fundamental to our understanding of physics itself, pushing the boundaries of general relativity, quantum mechanics, and nuclear physics. These magnetar quakes are not just dramatic events, they are cosmic laboratories, providing data on the most exotic states of matter in the universe. The purpose of a magnetar, cosmic architects. Now here's a philosophical question for a scientific topic. What is the purpose of a magnetar? In a purely anthropocentric sense, celestial objects don't have intentions or goals. However, in the grand cosmic scheme, every object and every event contributes to the evolution of the universe. Magnetars, with their extreme properties and violent outbursts, play a surprisingly significant, albeit indirect, role in shaping the cosmos around them. One of their primary contributions comes from their explosive birth. The supernova that creates a magnetar, or any neutron star, is a crucial mechanism for distributing heavy elements like oxygen, carbon, iron, and silicon, which were forged in the star's core, throughout interstellar space. These elements are the building blocks for new stars, planets, and ultimately, life itself. Beyond their initial explosive contribution, the powerful magnetic fields and high-energy radiation emitted by active magnetars can influence their local environments. While the exact extent of this influence is still being researched, it's plausible that the immense pressure from their magnetic fields and the intense bursts of X-rays and gamma rays could affect the density and temperature of nearby gas and dust clouds. This interaction could potentially trigger or suppress star formation in certain regions, acting as a subtle yet powerful sculptor of galactic landscapes. Imagine a cosmic beacon, not only illuminating the darkness, but also subtly stirring the primordial soup from which new celestial bodies arise. Furthermore, magnetars serve as invaluable natural laboratories for physicists. By observing their extreme behavior, scientists can test the limits of our understanding of fundamental physics. The sheer strength of their magnetic fields allows us to probe quantum electrodynamics in conditions far beyond anything we can create on Earth. Their incredible density provides data on the behavior of matter under extreme gravitational forces, helping to refine our theories of general relativity and nuclear physics. In essence, magnetars, though rare, provide unique data points that help us complete the universe's most complex puzzle. So, while they don't have a purpose in the human sense, their existence and behavior are integral to both the physical evolution of the cosmos and our intellectual pursuit of understanding it. Cosmic lighthouses, detectable across billions of light years. One of the most remarkable aspects of magnetars is their ability to make their presence known across truly immense cosmic distances. Despite being incredibly small, only about 20 kilometers in diameter, their energetic outbursts are so powerful that they can be detected by telescopes on Earth and in orbit, even when originating from galaxies billions of light years away. This makes them incredibly valuable tools for astrophysics, acting as cosmic lighthouses that illuminate otherwise dark corners of the universe. The specific types of signals we detect are primarily in the X-ray and gamma-ray parts of the electromagnetic spectrum, as these high-energy photons are the ones unleashed during their dramatic flares and bursts. The detection of these signals has led to the discovery of a relatively new and exciting phenomenon known as fast radio bursts, or FRBS. For years, FRBS were one of the biggest mysteries in astrophysics, incredibly powerful, extremely short bursts of radio waves, lasting only milliseconds, originating from distant galaxies. The source of these enigmatic signals remained elusive until very recently. In 2020, scientists detected an FRB originating from a known magnetar within our own Milky Way galaxy. This groundbreaking discovery strongly suggested, and in many cases confirmed, that at least some FRBS are generated by magnetars. This breakthrough transformed our understanding of these mysterious bursts and solidified magnetars as powerful probes of the distant universe. When a magnetar emits an FRB, that signal travels across the vast cosmic web, traversing intergalactic gas and magnetic fields. As the radio waves pass through plasma, they are dispersed. Different frequencies arrive at slightly different times. By analyzing this dispersion measure, astronomers can estimate the amount of electron density along the line of sight to the FRB, which in turn helps them determine the distance to the source galaxy and map the distribution of matter in the universe. Essentially, these magnetar-generated FRBS are not just signals, they are cosmic rulers and probes, providing unique insights into the properties of the intergalactic medium and helping us to better understand the large-scale structure of the cosmos itself. Magnetars and gravitational waves. A new frontier. While their electromagnetic bursts are their most well-known characteristic, magnetars also hold incredible promise for the emerging field of gravitational wave astronomy. Gravitational waves are ripples in the fabric of space-time itself, predicted by Albert Einstein and directly detected for the first time in 2015 by the LIGO experiment. These waves are generated by extremely violent and massive cosmic events, such as the collision of black holes or neutron stars. Given the extreme conditions within magnetars, their incredible density, rapid rotation, and the powerful dynamic nature of their magnetic fields, they are prime candidates for generating gravitational waves. One of the primary ways magnetars could generate gravitational waves is through their intense magnetic fields. As the magnetic field constantly stresses and deforms the star's crust, particularly during a star quake, These distortions could create small but measurable perturbations in space-time. Imagine a tiny, incredibly dense, highly magnetized object literally wobbling or twisting under the internal strain. While the gravitational waves from a single magnetar starquake would likely be too faint for current detectors to pick up, a massive, globally significant rupture could potentially generate a detectable signal, offering an entirely new way to probe the internal physics of these objects. Furthermore, if a magnetar were to experience significant and sustained oscillations following a major flare, these non-axisymmetric, non-spherical oscillations would also radiate gravitational waves. The search for these signals is a major focus for gravitational wave observatories like LIGO and Virgo. Detecting gravitational waves from a magnetar would be a monumental achievement, providing complementary information to what we learn from electromagnetic observations. It would allow us to hear the internal rumblings of these stars, offering a direct probe of their incredibly dense matter and the extreme dynamics of their magnetic fields, pushing the boundaries of what we can learn about these fascinating cosmic entities.
The slow fade, Magnetar's twilight years. Even the most extreme objects in the universe eventually reach their twilight years. For a magnetar, its incredibly active and volatile life is finite. The defining characteristic of a magnetar, its ultra-strong magnetic field, is not eternal. Scientists believe that the powerful magnetic fields of magnetars gradually decay over time. This decay is a relatively slow process on astronomical timescales, taking millions of years. As the magnetic field weakens, the magnetar's characteristic bursts and flares become less frequent and less energetic. It's like a cosmic battery slowly running out of charge, its once blinding flashes diminishing into faint flickers. The primary mechanism for this magnetic field decay is believed to be the dissipation of the internal currents that generate and sustain the field. As energy is lost through various processes, including the emission of electromagnetic radiation during flares and the conversion of magnetic energy into thermal energy, the strength of the field slowly diminishes. Over tens of millions of years, a magnetar that once boasted magnetic fields of 10 to the 15th Gauss might see its field strength drop by several orders of magnitude, eventually becoming indistinguishable from a regular, albeit rapidly rotating, neutron star or pulsar. This transition from an active magnetar to a dead or quiescent neutron star is a fascinating area of study. The once violent star becomes calmer, its crust less stressed, and its powerful bursts subside. It might continue to rotate rapidly, emitting regular radio pulses like a typical pulsar, but without the extreme magnetic field and the associated high-energy outbursts that defined its earlier life. The remnants of these once mighty objects persist throughout the galaxy, silent witnesses to their former glory, still incredibly dense, but no longer the extreme cosmic lighthouses they once were. Their magnetic legacy, however, continues to influence the interstellar medium, even in their dormant state. Conclusion: Legacy of Extremes. From their cataclysmic birth in the heart of a dying giant star to their long, slow fade into quieter neutron stars, magnetars represent some of the most extraordinary and extreme objects in our universe. They are cosmic paradoxes, tiny in size, yet possessing powers that dwarf galaxies. Their magnetic fields are so strong, they challenge the very fabric of matter, their outbursts so energetic, they can be seen across billions of light years. They are natural laboratories, pushing the boundaries of physics and forcing us to reconsider our understanding of matter under the most intense conditions imaginable. The study of magnetars is a vibrant and active field in astrophysics. Every new burst detected, every observed oscillation, every potential gravitational wave signal brings us closer to unraveling their deepest secrets. They remind us that the universe is far stranger,
more dynamic, and more powerful than we often imagine. Their existence highlights the incredible diversity of stellar endpoints, from the majestic beauty of planetary nebulae to the silent, terrifying embrace of black holes, and of course, the volatile, magnetic might of magnetars. As we continue to build more sensitive telescopes and develop more sophisticated gravitational wave detectors, our ability to probe these extreme objects will only improve. Who knows what other secrets magnetars still hold? Perhaps they will reveal new physics, entirely unknown phenomena, or provide critical clues to the grand puzzles of dark matter and dark energy. One thing is certain: the universe will continue to surprise and awe us, and magnetars stand as shining and often flashing testaments to its boundless complexity and raw power.